Okay, so new section for today, cross-product and determinant. One could argue that really our goal for today is to talk about cross-product. This is a tool that we'll be using significantly. But there's some really strong connections between cross-products and determinants. And I think y'all have probably seen some of determinants before. Usually determinant gets mentioned in high school algebra classes or somewhere along the line. But what you've seen of determinants is probably just a thin sliver of what there is to know about determinants. And I'm going to tell you more today, probably, but what I'm going to tell you today is a thin sliver of what I will tell those of you who take Math 216 about determinants when we take Math 216. And that is really just still the tip of the iceberg. I mean, it's a big, deep subject. There's a lot to say about it. Anyway, heads up about that. But it's a nice, like I say, it connects very strongly to cross products, and so I think it makes sense to talk about them at the same time. These two ideas, as it turns out, are also strongly connected to this third idea called right-hand order. And this is a kind of geometrically subtle idea to talk about. I'm going to start with this one. So there are different ways to approach these topics, by the way. Different books present these ideas in different orders. And that's a little weird, right? You're probably accustomed to, you got to know this before you can do that, right? And there's sort of a natural verticality to the way math is presented. And the thing is, it's really not... there is no unique way to, what comes before what, especially in this area. So I'm going to take an approach that emphasizes geometric intuition. There are lots of different other ways to go. If you want to be more rigorous, then you do it differently. If you want to be more sophisticated, maybe you do it a little bit differently, right? For Math 212, I think this is a good choice. Okay, enough preliminaries. Let's talk about right-hand order. Suppose I have a couple of vectors, v and w. Okay, there they are, two vectors. Now here's a refinement of that idea. Suppose I want to talk about the order that I write them down. So don't think of v and w as just a pair of vectors. Let's think of them as an ordered pair. Think of them as a list. When you have a list, one of them's first, one of them's second. So I want to talk about the list. So there are two different ways to turn those vectors into a list. I could do v comma w, I could do w comma v. And I ask, how would I distinguish these from each other? And the smart alecky response is to say one is in alphabetical order and one is not in alphabetical order. Okay, so that distinguishes, okay, fine, yeah, sure, but there's no geometric significance to that. Right? Okay, so labels aside, is there a geometric way of distinguishing these orders? And there's different ways you can go about this. I'm going to show you one that has some nice features. This is called clockwise versus counterclockwise. And the idea is this, whichever one is listed first, suppose I'm looking at the list v comma w. So that means v is first, right, and w is second. And the rule for deciding if this ordering is clockwise or counterclockwise is look at the direction defined by the first vector. Start with that direction. And then ask yourself, from that direction, there's the clockwise order. Here's the counterclockwise. I mean, y'all know clockwise and counterclockwise, right? So, question, which way would you rotate from the order defined by that first vector, the direction defined by that first vector? Which of these would get you to the w vector? And, well, in this case, pretty easy to see that the way you get to the second vector is by going counterclockwise. So, this listing, v comma w, is a counterclockwise order. So that listing counterclockwise because first to second is a counterclockwise rotation. Is everybody on board? Okay. Now, what's so great about this? Why can't, how about I just say, well, whichever one's further to the left We'll call that a left to right order or something, right? I mean, which is higher, which is lower. I mean, there's different ways you can go. Here's a unique characteristic of this distinct way of distinguishing orders. It doesn't matter how you turn the vectors, as long as you sort of turn them all together. If you were to take your head and kind of turn it around like that, no matter how you look at the page, you always get the same answer, right? So now, how impressed should we be with this? Whatever. It's not clear why we should care about this necessarily, but nevertheless, that is a kind of a non-trivial characteristic, right? No matter how you turn your perspective, you always get the same answer. This pair of vectors, this relationship of directions, if you will, is counterclockwise. And top to bottom, bottom to top, left to right, right to left, not so. Those don't have that feature. Okay. All right. So now here's the harder question. Oh, I'm sorry, getting ahead of myself. Here's a couple other characteristics about this order. If you have a listing that is in counterclockwise order, then if you switch the order that you write them down, switch V with W, right? Then the result, oops, I wanted to be in the highlighter mode. The result, highlighter mode, the result is in clockwise order. So switching the vectors always switches the order. Now that's just an observation. Again, it's not deep. Something you can kind of think through. If you go counterclockwise to get from V to W, well then you'd go clockwise to get from W to V. Okay. Here's another kind of neat observation. These are reflections of each other. And what I mean by that is, if you look at a pair of vectors, if you look at, let's say V comma W, right? And let's say, V is like that and W is like that. If you were to reflect them to come up with V prime and W prime, right? This being a counterclockwise order, the reflection is a clockwise order. So this is what we mean when we say that these two orderings are reflections of each other. And that's another sort of, there's a certain amount of geometric naturality. Again, not clear why we care, but there is something, you got to give it to me, geometrically interesting about that. Okay, so let's move on to the next question, which is, what if I have three vectors? Where did I write this down? Back up here. Suppose I have three vectors, but now in three space, right? So 1, 2, 3, something like that. So they're in space now. They're not just in the plane. Is there like a kind of sort of version of this sort of thing? Is there like a clockwise? Is there a notion of clockwise instead of for two vectors in two dimensions? For if I have three vectors in three dimensions, can I talk about something that has kind of analogous characteristics? A way of choosing the order that is somehow there's this reflection property, right? This property that when you switch any two of them, you get the opposite. Is there something like that? Well, this is a hard question, and I don't expect anybody to just come up with this on their own. This is a very clever insight. Here's how you do it. Suppose you have a listing of three vectors now, A, B, C. Again, it's about the listing. It's not just about the trio, right? It's the A is first, B is second, C is third. What can I give a geometric characterization of that choice of the order? Okay, so here's the idea. What we're going to do is we're going to first look at the first two of them. Those first two define a plane. Okay. All right. Then I'm going to say, well, let's look at that plane. And by the way, so you're going to have to use your hands on this, specifically your right hand. Notice right hands and left hands don't look alike. They look, well, in a way, they look a lot alike. They're not identical, right? If you were to cut off a hand and look at it, you could identify whether that was a left hand or a right hand. Okay. So, got to use your right hand. Put your index finger in the direction of the first vector. Your index finger, here's the rule, but this is an arbitrary set of rules here. Your index finger has to remain parallel to your palm, like you're shooting a gun, right? Index finger parallel to your palm. Okay. Now, put your middle finger in the direction of the second vector, and the rule here is you can only bend your middle finger the way middle fingers want to bend. So, no, what I like to call hand yoga, right? Don't do this. That's not fair. Right? So bend your middle finger the way your middle finger wants to bend. Now, you've already decided that your index finger is in the direction of the first vector, A. Right? Now, you can turn around that index finger however you need to. Right? So turn whatever way you have to, however much you have to, so that when you bend your middle finger the way middle fingers want to bend, you can get that second finger going in the direction of the second vector. Everybody on board? Okay. Now, when you do that, notice your thumb points a certain way. And again, no hand yoga. Let's not do anything like that, right? Your thumb, doing what thumbs want to do, is going a certain way. Specifically, though, looking at that plane that we were looking at, that plane defined by A and B, your thumb points on a well-defined side of the plane. That purple plane has, now in this case, just for description purposes, that plane has sort of an above it side and then sort of a below it side. Well, your thumb is pointing into the above it side. That's the thumb of your right hand, mind you. Right? So here's the rule. If the third vector is pointing on the same side of the plane as your thumb, doesn't have to be parallel to the thumb, it just has to be pointing on the same side of the plane that your thumb is, then we say that this listing ABC is a right hand order. So let me write this down again. So we're looking at A, B, C, A being first, B being second, just to emphasize, 3 being third. The first two vectors define this plane. Your right-hand thumb then defines a well-defined side of that plane, and that third vector may be or maybe is not on the same side of the plane as your thumb. Is everybody on board with how this breaks down? Okay. That's the rule. And now I appeal to your geometric intuition and your ability to hand wave. If C is not pointing on that side, let's see, do I have a picture? Let me just come over to here. Let's suppose C were pointing, hypothetically, on the other side. That's not a right-hand order. Right? I mean, so A, B, C, my thumb is pointing on this side, right? The C is not pointing to the same side of the plane, so it's not a right-hand order, but it is what you might reasonably call a left-hand order. And again, think about the thing. Okay, so let's do the same thing now, but with your left hand. Index finger in the direction of the first vector, right? Now I gotta bend my middle finger to go in the same direction as that B, second vector. How am I going to do? I'm going to do that by turning my hand as needed, so that when I bend my middle finger the way middle fingers want to bend, I can actually make it go in the direction of that B vector. And now look at my thumb with my left hand. It is pointing on the same side of the plane as the C vector. Okay, so roughly speaking, right hand order and left hand order are opposites of each other. Everybody see what right hand order and left hand order are opposites of each other. Okay. All right. Okay. All righty then. So a couple of neat observations to make about right-hand order and left-hand order. These three orderings. Let me zoom in. These three orderings here, ABC, BCA, CAB. They're all going to have the same ordering. They're either all right-handed or they're all left-handed. Now, I don't know which, right? It depends on the vectors. It depends on what A, B, and C are. But if ABC is a right-hand order, A, B, C, then look at this. See this move here? If ABC is a right-hand order, then this says that CAB is a right-hand order. And I don't think I have the wrist flexibility to do the other one, but it's just, this sort of a rotation. I think you can pursue. Let's just make it geometrically plausible. We don't need to prove this, right? But these are always going to be the same orderings as each other. Likewise, these three orderings are always the same as each other. And again, it's just this argument here. And I don't know whether they're all three right-hand or all three left-hand, but they're all three the same. And finally, not hard to persuade yourself that these three orderings that I have written down in blue that are all the same, these three orderings that I have written down in green that are all the same, these pairs are always opposite of each other. Right? So if ABC is a right-hand ordering, then ACB has got to be a left-hand ordering. Now, how can you see that? Well, again, it's a little hand-wavy argument. Let's suppose this is my demonstration here, that ABC is right-hand order, right? If that's ABC, well, this would be BAC being a left-hand order. So ABC and BAC are opposites. Does that make sense to everybody? I can't make my hand superimpose, but I'm trying to do this with my first two fingers, and then notice that because I'm using opposite hands, my thumbs are going the same way. Okay. All right. So another way to say this is if you have an ordering and if you switch two of the vectors like that, then the result is in the opposite order. So this has got that same characteristic that clockwise, counterclockwise had. You switch two vectors, you change the ordering. Okay, so that's kind of interesting. The other thing is these two orderings are reflections of each other. And this is, I think, really easy to see. Here you go. Let's look at my left hand and look at my right hand, and these are clearly reflections of each other. So this right-hand order, left-hand order business has all the geometric earmarks of clockwise, counterclockwise, just for three vectors in three dimensions. Okay. All right. Okay. So, what does this have to do with anything? We ask. By the way, this picture right here, this is the hardest picture in the book to draw. It took me like an hour and a half or something. It's harder than it looks to make a hand look like a hand. I was sitting there doing like this the whole time. Okay, let's see here. Next topic, determinant. Like I say, I think some of you all have seen determinants before. If you haven't, don't worry about it. No big deal. But here's the formula for a 2x2 determinant. If you have a 2x2 matrix, this little formula, AD minus BC, is what we call the determinant of that matrix. And the way people like to think about that, a memory tool, if you will, for the rule, is that you first go sort of down the diagonal to get that term, and then you come around over here and go down sort of the cross diagonal and subtract to get the other term. Okay. All right. Okay. If you have a 3x3 determinant, here's the formula for that determinant. By the way, you'll notice I'm using this notation here. Bars on either side of a matrix is an alternative notation for determinant. So the determinant of this 3 by 3 matrix, here's the definition. This is a weirder one. This isn't as convenient to write down, but here we go. It's a strange rule. We're going to go across the top row. For each term in the top row, we're going to write down that term. We're going to cross out the corresponding row and column. We're going to look at the resulting submatrix, and we're going to take the determinant of that resulting submatrix. And we do that all the way across the top row. So let's look at the next term. Would be we're going to look at the second entry on the top row. We cross out the row and column. Look at the remaining 4 entries. That makes a 2 by 2 submatrix, and we take the determinant of that. All right, etc. for the third term. Okay, the one little tweak is, and this seems strange to students, but there is a minus sign there. Don't forget that minus sign. That's a very important minus sign. If you don't put the minus sign in there, then this object, without that minus sign, the resulting object would be algebraically not interesting. It wouldn't have any interesting properties. Wouldn't be geometrically natural in any way. Wouldn't have anything to do with solving systems of equations that you've seen before in algebra classes. It's just not a thing. You gotta have that minus sign. So be very careful with that. It's so easy to inadvertently forget that minus sign. Okay, so that's a 3 by 3 determinant. Just out of curiosity, how many people have seen these formulas before? Several. Okay, great. All right. If you haven't, there they are. Okay, so like I say, some of you all have probably seen some properties of determinant. Here's one I bet you haven't seen. At least a lot of students have not seen this. It's a little hard to state this, but suppose you have a couple of vectors in R2. You got a vector A, you got a vector B. Let's just say. I'm going to make 2 things out of this pair of vectors. By the way, this is an ordered pair. A is first, B is second. Right, in fact, so first, second. Okay, the first thing I'm going to make out of this is I'm going to make a matrix by taking the first vector and making that the first row, and I'm going to take the second vector and make that the second row. Right? The second thing that I'm going to make out of these 2 vectors seems like a weird thing to do, but I'm going to take the first vector. Here, let me make an axis system over here. I'm going to take the first vector and the second vector, and out of the 2 of them, I'm going to make the what I'm going to call the corresponding parallelogram. All right. So out of these 2 vectors, I've made an algebraic object, namely a matrix. I've made a geometric object, namely a parallelogram. And here's the shocking fact. I'll write this down. I'll do this geometrically before I write it algebraically. The area of this parallelogram relates to the determinant of the matrix. Well, let me just circle, say the determinant of that matrix. So that's very, very weird that the determinant, look at how we define determinant. It's algebraic, purely algebraic. 3-function arithmetic. Add, subtract, multiply. We're not even dividing. 3-function arithmetic, and we're computing an area of something that has wacky angles in it, and the lengths are square roots and all of that business. That's very surprising. Okay, so let me get to where we can write this down. Okay, so specifically, the area is equal to the determinant. The absolute value of the determinant. So, very surprising. But that's not all. There is another neat fact, and that is the ordering. So keep in mind, now A is first, B is second. That ordering, A first, B second, is either clockwise or counterclockwise. How do we decide if it's clockwise or counterclockwise? Well, do we have to, one would think, draw the vectors and look at the picture and think about it geometrically? Turns out no. The ordering is also decided by the determinant in terms of whether it's positive or negative. Whether it's counterclockwise or clockwise is decided by whether the determinant is positive or negative. Super weird. I'm not going to prove this result in this course. There's a couple different ways to prove it. One is highly geometric and involves a lot of trig and cranking stuff out, and it's ultimately perfectly rigorous and fine, and I have nothing against it, but it's kind of opaque. It's not very satisfying. I don't think students walk away from that ugly proof having really learned something. Right? Now, there's a better way to prove this fact, but it uses sophisticated ideas and tools that we haven't developed in this class and that we're not going to. It's too much to do in Math 212. I've done it before in Math 221. And it's just a more sophisticated class. It's different focus. Okay, so I'm just not going to prove it at all. I'm just going to assert that this is true. And anyway. Okay, so there's a third case here. You'll notice I didn't address this third case. That is if the vectors are in neither order. And let's just think about, what could that possibly look like? How could you have a pair of vectors that's neither clockwise nor counterclockwise? Looking back at this picture here, neither one nor the other. That would come about if the two vectors are parallel, right? Either way, either direct parallel or opposite parallel, right? Or if one of the vectors were the zero vector, or hypothetically, if both of the vectors are the zero vector, something annoying like that. If either one of those happens, then it's not clockwise and it's not counterclockwise. That's what we call a neither, right? If the ordering is neither, when you think about these cases, right? A case that looks like this, for example, neither clockwise nor counterclockwise. Notice that the vectors are parallel, or one is a multiple of the other, depending on how you want to say it. Okay. All right, so if that's the case, going back to this theorem, if neither happens, then the determinant will be 0. And, of course, if the determinant's 0, let's think about, what's the area? The area in such a case, if the two vectors are parallel, the area of the parallelogram would also be 0. And so this pattern holds. The absolute value of the determinant is equal to the area. Okay. All right. Okay. So this is the two-dimensional version of this theorem. There's a three-dimensional version of the theorem, and it's exactly what you would guess if you have three vectors. And if on the one hand you make, I guess I have to zoom out one notch. If on the one hand you make a matrix by first vector, first row, second vector, second row, third vector, third row, make a matrix. Geometrically, you take the first vector, second vector, third vector, make a parallelogram. What do we call this thing? This is called a parallelepiped. It's like a three-dimensional version of a parallelogram. Make this object. Then the ordering, whether this is a right-hand order or a left-hand order, is decided by whether the determinant is positive or negative. This, again, is exactly what you would expect based on the analogy to the two-dimensional version. And the volume of that parallelepiped, that volume there, is equal to the absolute value of the determinant of that matrix. It's the same, close as you could possibly get to being the same, adapted appropriately given the three-dimensional context. Pretty much the exact same theorem. Okay, all right, so here's an example just to show you how this works in practice. Here's a trio of vectors, in fact, in an order. And let's ask two questions. First of all, is this listing of vectors right-hand order or left-hand order? Well, it's really hard to tell at a glance, right? I guess you could plot all three vectors, and if you had like a three-dimensional model that showed the actual vectors, then you could see those three vectors and decide, is this vector, which side is, how does that plane defined by those two vectors, and where is this one on which side of that plane is it on? But you really need to have a three-dimensional model. If you just sit there and work it with a pencil, it could be really, really hard to tell. So we can decide very quickly by taking those three vectors, 1, 2, 3, making those the three rows, 1, 2, 3. We compute the determinant by the usual formula. We see that the determinant is negative. Negative means left-hand order. If it had been positive, it would have been right-hand order. So determinant decides that for us. So determinant has a pretty cool geometric connection there. Everybody happy? Okay. All right. Likewise, the original question, what's the volume of the parallelepiped? Well, the volume is the absolute value, which is 10. Okay. All righty. Okay. All right, moving along. Cross product. So we've talked about right-hand order. We've talked about determinants. Both of these things are very, very strongly connected to cross product. I'm going to define cross product kind of analogously to how I define dot product. Namely, I'm not going to start with a geometric motivation and then derive a formula. I'm going to start by writing down an arbitrary formula seemingly pulled out of thin air. At which point I now owe you satisfaction that this is somehow interesting and not just a made-up, meaningless bunch of nonsense, right? So now I'm going to spend the rest of this section trying to satisfy you on that point. Anyway, here's the formula. Do notice that one big piece of good news: the cross product of two vectors is now another vector, as you kind of would have expected an operation on vectors to be, right? So that's good. Here's a bunch of properties. Now, students, as you may recall, you may have even experienced this yourself. When you see, here are the algebraic properties of our new operation, there tends to be kind of an eye roll. Well, of course, they're always the same properties. Why do we have to write these all down, for crying out loud? This is a great example of why you got to be really careful. You can't just, I've just defined something. I'm calling it a times, therefore it must behave like all other products do. This doesn't. This is super weird. The first one is the weirdest, I think. This cross product is not commutative. There's a minus sign there. Whoops. That's just the way it is. So, again, this is why you have to, care about proving properties. Not everything behaves the way you would sort of expect. Okay. All right. This is easy to check, by the way. Okay. Okay. Here's some others. The second one's not terribly surprising, I suppose. It is a little weird, though. This is, I'm going to take a dot product with a cross product of two vectors. And the strange thing about this is that what we're doing here is we're not like trading these two positions or trading these two positions or anything like that. What we're doing is kind of cycling through. So the first vector listed goes to the second spot, and the second vector listed goes to the third spot, and then the third vector listed goes to the first spot. Right? Here's another way to think about what we're doing here. It's like we have the vectors written down, u, v, w. Think of them as if I had them written in a circle. This u, v, w, we're going around the circle of 3 vectors. And then what we have over here, w, u, v, goes around the circle in the same order, just starting from a different place. However you want to think about it. Okay, so result, though, these 3 things are all equal to each other. And not terribly too surprising, but keep in mind, it's only these 3. If you were to change these 2 things, if you were to change the v and the w, well, you'd get a minus sign. Right? So of the 6 different orders that you can write these 3 vectors down, 3 of them in this construction, 3 of them give you the same result, 3 of them give you the opposite result. Okay. Whoops. So last one, and this is geometrically pretty interesting, but there's a better way to think about it. If the cross product is 0, the vectors are parallel, or there's some anomalous, annoyance, like one of the vectors is 0. This is vaguely reminiscent of a property of dot products. Y'all remember dot product? If the dot product is 0, the vectors are either perpendicular or one of the vectors is 0. Cross product is 0, parallel. Okay. Okay. Alrighty. All of these can be proved by direct algebra, which has its merits, I suppose. But also, all of these can be thought of in certain convenient geometric ways. And I would like to show you all the geometrically natural, the geometrically satisfying ways to think about these properties as we go along in the section here. Okay, so first up, another property of cross products. The cross product is always orthogonal to both of the input vectors, both v and w. Give me any 2 vectors. The cross product's orthogonal to both of them. That's a pretty neat trick, by the way. You give me a couple of vectors, here's a couple of vectors. How would I go about finding a vector that's orthogonal to both of them? Okay, it's tricky. Cross product does that. This is a proof that I'm going to let you all do on your own. It's pretty straightforward. If you want to show that 2 vectors are orthogonal, the way you show that 2 vectors are orthogonal is you compute the dot product and you confirm that you get 0. Right? So if you want to show specifically that V is orthogonal to the cross product, then there's a dot product that you need to compute and show that you get 0. And it's just not that hard to do this. Think about this this calculation here. How would you go about computing this expression? Well, we have a formula for cross product. We have a formula for dot product. Crank it out. It's just plug and chug. It's not even all that bad if you think about it. Neither one of these formulas is particularly terrible. The cross product formula, I will confess, the cross product formula has 6 terms, right? But it's just 6. It's not 600, right? So you write down those 6 terms. You do a dot product. You have 6 terms. They cancel. It's pretty quick, actually. Okay, so I think that's a healthy exercise. I want everyone to take a shot at that. Likewise for W, by the way. W also. W is also orthogonal, and you get that by doing that dot product. Okay. All right. Okay. Here's some algebraic observations we have to make. These are not so much calculations as observations. I think these are really valuable. Let me go back real quick. Here's our formula for cross product. Whoops, wrong mode. Cross product. Notice each one of these coordinates, something times something minus something times something, each one of these coordinates looks like a 2 by 2 determinant. It's just an observation. In fact, if you were to write down those coordinates, the first coordinate is that 2 by 2 determinant. Here, let me do this. It's that 2 by 2 determinant. The second coordinate is that 2 by 2 determinant with a minus sign. It's a little weird, but that's how it works out. And then the third coordinate is that 2 by 2 determinant. Now notice I'm writing a vector by writing that vector as a linear combination of the standard basis vectors. All this is a fancy way of saying that the coordinates of that cross product are the green number, then the blue number, then the purple number. Those are those three coordinates. Okay, so that's an observation. Now, here's another observation. That expression there, just cosmetically now, looks just like our definition of a 3 by 3 determinant. Doesn't it? Something times a determinant minus something times a determinant plus something times a determinant. It looks the same. Oops, ahead of myself. Same exact structure. So now this is going to seem a little bit cheating, but I'm going to do this anyway, and then I'll confess later. This, looking as it does, like a 3 by 3 determinant, let's write it as a 3 by 3 determinant. Now, confession. Matrices are supposed to have, as the entries, they're supposed to have numbers. There is a pretty ugly question of are you allowed to put a vector as an entry inside of a matrix? Is that appropriate? Can you do that? Right? So, okay, that is a concern. I'm going to correct that by just saying, look, from a symbolic point of view, and let's not worry about, is that really a matrix? And it's not what that's not where we're going to go with this, right? What I want y'all to do with this result formula here is to use this as a memory tool. This is a fantastic memory tool. This is how I, for my entire life, have memorized the formula for the cross product. The cross product is what you get when you take the first vector, put it there, you take the second vector, and you put it there. On the top row, you put the standard basis vectors, and then just play the determinant game. Right? I had to already memorize the formula for determinant anyway. This is a really simple little structure to think about, and it automatically keeps track of the signs for you and everything. So this is the formula that I encourage you to memorize. Related note, this formula here for cross product, never in my life have I memorized this formula. Not even when I was a college student, like taking classes like y'all are. I never memorized this formula. I wouldn't trust myself. I'd get it wrong. Somewhere along the way, I'd need to compute this second term, and I'd be like, oh God, is it V1W3 minus V3W1, or does it go the other way? Which way? Right? You're gonna forget. It's weird. Right? This keeps track of that for you. So that's my strong urge for y'all on that formula. Now here's another neat fact about determinants. If you look at, do it like this. If you look, I guess I'll zoom. It's fine. Let's look at this expression. What I'm going to call a triple product. A dot product with a cross product, right? We saw this on our list of algebraic properties previously. Look at that expression. There's an easy formula for this triple product. That triple product, notice it's the cross product I have here. The coordinates of the cross product, there they are. Here's the coordinates of the cross product. and I'm multiplying them one at a time and adding, namely doing a dot product, with the coordinates of u. So just another kind of clever observation that, as it turns out, this triple product structurally also looks just like a 3x3 determinant. It's got that same, number times a determinant, number times a determinant, number times a determinant, with this mysterious minus sign on the second term. So that too is a determinant, and that gives us this formula here. This triple product is a determinant. Or the way I like to write it, a little sort of a shorthand for the same thing, is this triple product construction: first vector, first row; second vector, second row; third vector, third row. Okay. All right. Everybody on board? Okay. Right. So this formula is going to be super powerful for us. Let me give you a quick plausibility argument. Why is it that we're going to be able to do so much with this formula? And the answer is we already know some neat geometric properties of the determinant. It relates to volume in a really surprising way. That's powerful. Right? We also already know some neat geometric properties of the dot product. Right? And the relationship then between these three things, if I already understand two of the three operations involved in this formula, it's going to help me understand what I want to understand about cross product. Okay, so that's strategically, that's how this is going to break down. Okay, all right. So alrighty, let's go back a page. We've made the observation that the cross product is always orthogonal, right, to the two input vectors. How did I persuade you that this is true? Well, I made a bluntly algebraic appeal. I said, look, orthogonal means, orthogonal means that you compute the dot product and fingers crossed hope you get 0, and off you go, plug and chug, right? Purely algebraic. Now, there's something nice about algebraic arguments. Algebraic arguments are bulletproof, right? If you've done the algebra and just algebraically, look, what are you going to argue with? You're going to claim algebra doesn't work? Right? Algebra is solid, right? But it's also kind of opaque. It's unsatisfying in a way, in that, the way I like to say it is, you can believe with algebra that something is true, but it never really gives you satisfaction with why something should be true, right? And so algebra, again, I'm a big fan, don't get me wrong, but satisfaction, intuition is going to come from other things, I think. So I'm going to try to give you an intuitive argument about why should the cross product do orthogonal to both of the input vectors. So here's how the argument works. We're going to look, for example, at this dot product again. Now, again, I could just crank it, right? But let's think instead about, what else do I know about that dot product? Well, this dot product, look at what we're taking a dot product of. We're taking a dot product of a vector and a cross product of two other vectors. We're taking a triple product. And what we just saw over here is that triple products are determinants. How about that? First connection. Triple products. So let's say it this way. The dot product in question is a triple product, and triple products are determinants. Well, I also know, side note, that triple products are volumes. Absolute value. Sure, right. So, first vector, second vector. Okay, now wait a minute. That first vector and the second vector, they're both V. Is that right? I mean, does this make sense? Is this a typo? V and V? Well, yes, it is. This is perfectly fine, because look, the whole point is I'm trying to argue that this cross product is orthogonal to the first vector in the cross product, right? So it is deliberately the case that these first two vectors are both V. That is not an accident. So, first vector V, second vector, here let me not do that in blue. Second vector, also V. And then, okay, fine, the third vector is W, that's some other vector. Like that. Okay. Now, these three vectors over here, geometric appeal, I've got, three vectors. Remember, we've got to take these three vectors and make a parallelepiped out of them. What's that parallelepiped going to look like if the first two vectors are the same vector? Well, it's going to be a box, but it's going to be a smushed box. It's a box that's flattened for recycling, right? I mean, these two vectors are the same vector, and so, yeah. Does that make sense to everybody? Everybody happy with that? How much volume is there in that box? 0. It's flat. Okay, so no volume. The volume is 0. That means this determinant is 0. That means this triple product is 0. That means this dot product is 0, and that means these vectors are with volume. Let's see how that works. I love this proof because it connects so many geometrically natural ideas all in one quick little argument. Yeah.
Sorry, what's this in the diagram? What's like the second part of the box? Like there's the VW.
This right here?
Yeah, there's the VW, and then there's like I guess another not like it's like divided up into two parts. I'm just curious for the second part.
So this is my attempt to draw the box that you would get if you took. So if you have three vectors and you make a parallelepiped, right? You're going to get what I'm calling a box, right? Now, I like to equate this process of imagining these two vectors as becoming the same vector. Think about, like if you have an actual cardboard box, or you ordered something on Amazon, and you open it up, and then you gotta cut off the bottom or whatever, loosen it up. You know how when you fold it for recycling, right? When you fold that box for recycling, it's going to look something kind of like that.
And what's the line in the middle going from like the head of B to down to
from here to here?
Yeah.
Well, that's the recycled box. I mean, honestly, I should have brought in a box. I've got a million of them. But here, imagine this is a square, right? This is my box, right? I've already cut off the top and the bottom, and there's four sides. I have two palms and two sets of fingers that are the four sides, right? Well, when I do this, you got the two palms that come together, but you also got the two sets of fingers that come together. So these are the two palms, these are the two sets of fingers. Does that make sense?
Yeah, perfect.
Yeah. All right. Anyway, kind of a cool proof. Okay. Here's another one. This is hard to see coming. A little bit of notation I made up by the way. So I'm going to use this notation right here. You see the two parallel lines? Two parallel lines followed by a list of two vectors V and W. I'm going to use that notation to represent the parallelogram defined by those two vectors. I'm kind of proud of that. I think that makes a lot of sense. It's very compact. It's very elegant. I hope it catches on. I'm going to take credit for it if it does. Anyway, so that notation represents the parallelogram defined by those two vectors, and the area of that parallelogram defined by two vectors is the length of the cross product. Hard to see that coming, right? Why should that be true? Now, again, look. One thing you can do is you can brute force this. You can take a deep breath and write these down in coordinates and start plugging and chugging and using trig identities and all this kind of stuff, and it works out. It does. You can do it that way, but it's a horrific algebraic inconvenience for one thing. And for another thing, where's that satisfaction? Why should this be true? You don't get that. Okay? So let me make a geometric argument here. This is another what I like to call mathematical bank shot. I'm going to show that this is equal to this by considering a third object that is neither one of them. Right? We're going to start off by thinking about this determinant, for no apparent reason. We're going to look at the determinant of the matrix that you get by listing V cross W, then V, then W. Just bear with me. Okay. And it's going to turn out that by contemplating this, indirectly, it's going to turn out that we'll be able to prove this. So we're going to get over there by starting going in that way, and that's the term bank shot. Okay. All right. So let's think about this determinant. What can I say about this determinant? First observation I want to make about that determinant is it is a triple product. First vector dot second vector cross third vector. Right? Does everybody see how I'm just observing? Let me zoom in here. I'm just observing here how, triple products are determinants. This particular determinant is that particular triple product. Having observed that, now I also notice that, differently, notice that this is a vector dot itself, and a vector dot itself is magnitude squared. So that's the first half of my argument. Haven't proved my result yet, but bear with me. That's the first step. Next thing I'm going to do with this same determinant is I'm going to observe, we already know, that determinants are volumes. Right? So first vector, second vector, third vector. And this determinant is this volume, right? And I'm going to compute that volume now in a different way. Neat observation to make about this volume. Keep in mind, we've already showed that the cross product is perpendicular to both of the other vectors. So this is not just a random parallelepiped. This is a parallelepiped, which is a parallelogram and then a perpendicular vector to that parallelogram. And so the volume has an easy formula here. This volume in there is that height, magnitude of V cross W, times this area. Here, let me just say times the area of that parallelogram. Yeah? Questions? Very good. Okay. All right. So here's what we've got then. Here's this determinant that I don't actually care about. I've computed this thing that I don't care about two different ways. Having computed this thing that I don't care about two different ways, one conclusion I get is that the two results must be equal to each other. So these two things are equal to each other. Let's write that down. These are those two things being equal to each other, and look what we got. Indirectly, everything has just fallen in our lap. We just cancel this factor of length of the cross product, cancel that with that, one of those factors of length of the cross product, and as we were hoping, the length of the cross product is equal to the area of the parallelogram, and it just kind of falls in our lap. Isn't that clever? Everybody happy? Okay. All right. So, neat fact, and I think also a really neat proof. Another thing I like about this proof, just like the previous one, this uses a lot of these ideas with determinant and cross product that we discussed earlier in the section. Sort of, this brings it uses a lot of tools all in the same argument. That's neat. Okay. So. Let's go up here. So I'm going to ask a question: which direction does the cross product point? And we kind of have a lot of that question answered already. Let's remind ourselves. We know that given a vector v and a vector w, I know that the cross product is perpendicular to both of them, so therefore the cross product's got to be. There's this line. There's this single direction that is in fact perpendicular to those two given vectors. Right? Two vectors. There's only one direction left, if you will, that's perpendicular to both of them. Okay. So the question that remains, though, is, well, wait a minute. Does the cross product point that way, or does the cross product point that way? Which is it? There's two possibilities that are both perpendicular to both of the input vectors. All right. Okay. So which is it? Well, there's a great way to answer this question, which comes about by looking at this equation right here. And what this equation tells us, among other things, notice that this is positive. Well, it's not negative. If it were zero, by the way, I'll point out that we actually don't really care, because think about the scenario where this magnitude is zero. If this magnitude is zero, that means that the magnitude of the cross product is zero. That means the cross product is the zero vector. I don't need to decide which of two ways the zero vector points. The zero vector doesn't point at all. Right? So as far as we care, we can consider just the case of this being positive. If this is positive, that tells us right away that this is a right-hand ordering. So cross product V W, that is a right-hand ordering, because that determinant's positive. Okay, so cross product V W is a right-hand ordering, and the way that we're going to let me zoom back out. The way we're going to take advantage of that is to notice that this ordering, you'll notice cross product V W. Just cycle that list of vectors. Remember, you're allowed to cycle and it doesn't change the order. So V, comma W, comma cross product is always a right-hand order. So that answers our question. Which way does the cross product point in this picture here? In this picture, well, look at V, look at W. Right hand, right? First vector in the direction, or first finger in the direction of the first vector V, second finger in the direction of the second vector W. Your thumb tells you which way the cross product points along that line. So the cross product has to be, in this case, that way, not this other way. So what's nice about this is we now actually have a completely geometric characterization of the cross product. And this is, I think, very satisfying. We started off with a purely algebraic definition of cross product. Cross product is formula. Algebra, right? And now, here's what I can say. The cross product is the unique vector that's orthogonal to both of the input vectors, has length equal to the area of their parallelogram, and that satisfies the right-hand rule. There is always exactly one vector that satisfies those three rules. And there are some linear algebra textbooks that will define the cross product like that. It's a geometric definition of cross product, and then they can work from there and try to derive what the formula is. That's kind of cool. Okay. Alrighty. Okay, now this section always slows me down quite a bit. The next section, good news, does go relatively quickly. So let's try to make as much progress as we can into section 1.5 before we have to call it quits. Lines and planes. I hope you all remember this equation for a line in R2, y equals mx plus k, right? Everybody remembers that one? This was my favorite formula when I was in middle school. Favorite formula for a line? right? Because m meant something, m is the slope. It's geometrically meaningful, right? K meant something. K is the y-intercept. It's geometrically meaningful. I can deduce something about the line just by looking at the equation. Okay. Then they also showed me this equation. Ax plus by equals c. And they didn't give me any particularly satisfying geometric interpretation of, what does A mean? Right? I mean, there's just nothing. So, given my choice between these two, well, I like this one. I didn't like that one. Because it just seems like, I mean, what's the merit of this second equation? What does this equation have going for it? And the only thing I could think of was, I guess all the variables are on the left. It's organized or something, right? But that's not that persuasive. Okay, what I'd like to do now is show you how this is actually geometrically natural in ways that they don't tell you in middle school or high school, at least not in my high school. Okay, so what we're going to do is we're going to consider how to decide if a point is on a line. Here's my line. I'm going to describe the line to you by the following information. I'm going to give you what I'm going to call a normal vector n that is perpendicular to the line. Whoops, I'm sorry, my elbow hit the thing there. I'm going to give you a normal vector perpendicular to that line, and I'm going to give you a color choices. I'm going to give you a point on the line. Now, I appeal to your geometric intuition. If I tell you, hey, I'm talking about the line that's perpendicular to n and that passes through that point x naught, well, there's exactly one line that is perpendicular to n and passes through x naught, right? I mean, these are the only lines that are perpendicular to n, and well, exactly one of them is going to pass through x naught if I can draw competently. There we go. Okay, all right. So, using only these two givens to describe the line, how would I decide if a vector x is on the line or not on the line? Right, these are the two possibilities for x. Either it is on the line or it's not on the line. Okay, and the way you can argue this, I think it's a clever argument. Think about x minus x naught. Right? Notice that if the point x is on the line, then x minus x naught is parallel to the line. And I remind you of the distinction between parallel and on and in and all that business. So x being on the line means the difference is parallel to the line. Parallel to the line means perpendicular to the normal vector. Perpendicular means dot product is 0. Let's write all this down. X is on the line if the difference vector is parallel to the line, aka perpendicular to the normal vector, aka this dot product is 0. And if you write down that dot product and just do a little bit of algebra, you can distribute the dot product, move terms around, move this term here over to there, and notice that we were given n, we were given x naught. That was all given. And so we have ourselves a point tester. If you are interested in some vector x, and you'd like to know, is that point on the line? Well, all you have to do is just plug into this equation, compute n dot x to see if that's equal to n dot x naught. If it is, then just trace back through the argument. We know that x has got to be on the line. And if it's not, right, well then again, trace it back through the argument. If these two dot products are not equal, then it's not on the line. Okay. All right. So what does this have to do with ax plus by equals c? Well, if I were to choose to call these coordinates x and y, as of course I would, and if I were to choose to call the coordinates of n a comma b, then that dot product becomes ax plus by. Or said differently, looking at this equation, ax plus by equals c, there is a natural geometric interpretation of these numbers a and b. And again, they did not tell me this in middle school or high school. A and b can be interpreted as the coordinates of the normal vector, namely the vector perpendicular to the line. That is geometrically natural. Geometrically meaningful. Okay. Everybody on board? All right. So, why are we talking about lines in the XY plane? Well, this is a warm-up to an analogous argument that we're going to make for planes in space. So now let's think about planes in R3. We're going to make an analogous argument. Here's the picture. Suppose I am interested in a plane, and I'm going to describe the plane to you by giving you the normal vector, a normal vector perpendicular to the plane, and a base point in the plane. And I claim that those two pieces of information uniquely characterize a plane. There's exactly one plane that is perpendicular to n, and that passes through that point x naught. How would I decide if a point x is in the plane or not in the plane? Same game. In or not in corresponds to these difference vectors either being parallel or not parallel to the plane, which corresponds to being perpendicular or not perpendicular to the normal vector, which means the dot product is 0 or not 0, as the case may be. Right? So you can go through that same exact argument. Here's how it looks algebraically, and notice you get to a seemingly analogous looking punchline: n dot x equals n dot x naught. Again, what do these things mean algebraically? We're testing points x, y, z. This original normal vector, suppose it has coordinates a, b, c. And you get this equation for a plane in space. So ax plus by plus cz equals, whatever this right-hand side is, some constant d. So, analogous geometric interpretation. When you look at the equation of a plane like this, these numbers, A, B, and C, they're not just arbitrary numbers that, we had some other meaningful equation for the plane and we just kind of shove everything over to the left just for organizational purposes, and that's just kind of whatever you got. A, B, and C are very natural geometrically. A, B, and C tell you the coordinates of the normal vector to which the plane is perpendicular. So that's cool. Okay. All right. Okay, so a quick example. Suppose you want to know the equation of the plane, and it passes through that point. I'm going to use that as my x naught. And it's perpendicular to this vector. I'm going to use that as my normal vector. Right? And then you just write down n dot x equals n dot x naught. Notice that the n are the coordinates, the coefficients in front of the x, y's, and z's. Right? And then, you do have to crank out the dot product on the right-hand side. So n dot x naught, some value. And there you go. Here's your equation of your plane there. Okay. Cool. There's various twists on this. Suppose instead of giving you a normal vector, suppose I give you 3 points in the plane. Now, geometric appeal. If I were to give you 3 points in the plane, there is a unique plane that passes through those three, unless you get unlucky and they all kind of line up or something, unless there's a syzygy of points. right? But most of the time, if you give me 3 points, there is a unique plane that passes through those 3 points. Okay. How would you find the equation of that plane? Problem: I don't have a normal vector. I do have an x naught. I am flush in x naughts. I could use either A or B or C, whatever. Who cares? I just need any old point in the plane. Doesn't matter. Pick one, right? But to find a normal vector, the clever idea is to use a cross product. Notice that B minus A and C minus A are both parallel to the plane. We know that their cross product is perpendicular to both of those parallel vectors. And if that cross product is perpendicular to both of the green vectors, then the cross product is also perpendicular to the plane, and I can choose that cross product to be my normal vector n. Right, so that's the algebra that we have here. I'm going to choose n to be the cross product of these two difference vectors, b minus a and c minus a. And there you go. Okay. We're out of time. I guess this is where we're going to call it for today. Let's see, what page is this? 37. All right. So fall a little bit behind schedule. Try to catch up the next few days. All right. See y'all later.